Hey, today I will finally give you the definition of TC, topological cyclic homology. In fact, I will give you two equivalent definitions. The first one will be as an abstract mapping spectrum in the stable infinity category of cyclotomic spectra. And the second formula will be in terms of a concrete fiber between maps between TC minus and TP. The latter formula is the one which is really useful in computations, as we will see in the next video. And the former definition in terms of a mapping spectrum is very useful for theoretical purposes. Hi, I'm Thomas Nikolaus from Mathematics Münster. In order to give the definition of topological cyclic homology, let's remember in the last video of this lecture course on topological cyclic homology, which was video 13 and called the cyclotomic structure, we explained what the cyclotomic structure on TC is and what was that on topological Hochschild homology is. And that was for every prime number P, so P will always be a prime. A map, a T equivalent map, T was the circle group, variant map from THH R is any ring spectrum, into THH R Tate CP. And here this is a spectrum with a T action. And this a priori has a T mod CP residual action, but we identify T mod CP with T. So that was what the cyclotomic structure was on THH. And I mean, the definition then simply was the following. A cyclotomic spectrum is a spectrum with T action X in spectra with T action together with T equivalent maps from X into X Tate CP, which we denoted phi P for every prime P. Okay, so that's what a cyclotomic spectrum is. And remember, this T, for those of you who know equivalent homotopy theory, this is not equivalent in any sense. This is the most naive notion of T equivalent, just an infinity categorical functor from BT to X. And then, of course, I mean, this is what the object, what a cyclotomic spectrum is, and of course there's an infinity category of cyclotomic spectra. And so how is this defined? The infinity category of cyclotomic spectra, I mean, just the obvious infinity category you'd write down, having those objects, I guess, and formally this is a pullback defined as the pullback we denote it as cyc spectra for cyclotomic spectra. And so what is it? A cyclotomic spectrum consists of a spectrum with T action and a bunch of maps. So for every prime P we have a map of spectra with T action, so object in spectra BT to the delta 1. So the arrow category where P runs through all primes. And then, I mean, this has to have as source our initial spectrum and as target the Tate construction. So this goes to P, SP, BT, cross SP, BT, where this map is just the map which sends, I mean, it's an infinite family of identity, comma, blank, Tate CP. Over P. Right, so the functor, it somehow sends a spectrum with T action X to the family, which in the P coordinate is X, X Tate CP. Right, and this map is just a source cross target. So evaluation, I guess, well, let me write 0, evaluation 1. I guess in simplicial notation it would be 1 and 0, but this is just source and target for the arrow category. Okay, and also like, of course, P and P. Like the product of all those maps. Okay, so that is the infinity category of cyclotomic spectra. And in other words, in particular, let's just sort of spell out what a map is. A map of cyclotomic spectra well, X with Frobeni phi pi to Y with phi pi prime. Right, well, this is a family for every prime, but let me not use the family bracket notation, is given by the following datum. First of all, you have a T-equivalent map X to Y, and secondly, you have a homotopy, a T-equivalent homotopy. So in other words, a two-morphism in the infinity category of T-equivalent spectra filling the square. Well, what can you do? You can go from X, if this is F, can go to Y, and then you can go to X Tate CP with phi P. And here you can apply F to the Tate CP. So that will land you in Y to the Tate CP, and here you apply the phi P prime. Right, so there's two ways to go here, and so what you want to do is you want to fix a homotopy, and that for every prime P. And I guess this is the obvious notion of morphism. If you're not completely solid with pullbacks of infinity categories, it's a good exercise to deduce this from this pullback description. So the idea is to just note that in a pullback of infinity categories, the mapping spaces are pullbacks. And then if you spell this out, you get that. And in fact, we can make a stronger statement about the mapping space, which goes as follows. The mapping space is given as the mapping space in cyclotomic spectra from X to Y, and I guess I again mean X with phi P and Y with phi P prime, but let me suppress this in the notation and just write X to mean the cyclotomic spectrum, including all the additional structure, as is customary. So you have a map to the mapping space in cyclotomic in spectra with T action, X and Y. So this is just, we forget the cyclotomic structure and just consider X and Y as spectra with T action. And then there are two maps. There are two maps to the mapping space from X to Y Tate CP in spectra with T action from X to Y Tate CP. And what are the two maps? Well, you can just take a map here, F, and post-compose with phi prime. So that's maybe the first map, phi prime lower star. And then you can also take the map to the Tate CP and precompose with phi p. So let me just write this, abbreviate this as phi p upper star. So it's really first raising to the Tate CP and then post-composing with phi p. And these are the two maps, and I should say given as the equalizer. So this space is actually the equalizer of this diagram of spaces. And in fact, can say a little bit more. And that is the following proposition. Well, first part, cyclotomic spectra is a stable infinity category. And that is something which I want to leave as an exercise for you. The way to do that is to describe what limits and co-limits look like and check that it's stable. Okay, I won't say much more than that. And formula star holds for mapping spectra. So the moment you have a stable infinity category, you have mapping spectra, which we typically denoted with little map, and then we just can replace this with little map. And this is clear if you have it for big map and you have stable infinity categories and everything is exact. Okay, so that's the first statement. The second statement is actually more generally, like a stable infinity category has finite co-limits and limits. And the statement is cyclic spectra has all limits and co-limits. And this is actually much harder. So co-limits are easy. If you for the first part have worked out what co-limits are, then I mean this is the same. Co-limits are underlying, but limits are complicated. And in fact, for the experts, the way to show that is actually to show that it's a presentable stable infinity category, and then it follows formally that it has limits. So, right, so the way to prove this second claim, which I will not do, is to prove a slightly stronger claim. The next claim is that cyclic spectra has a symmetric monoidal structure. Monoidal structure given by, well, I guess we're just saying that if I have a cyclotomic spectrum x phi p and I tensor it with a cyclotomic spectrum y phi p prime, then what I'm going to do is I just take the underlying tensor product x tensor y with the diagonal t action. And then how is this a cyclotomic Frobenius? Well, I'm just going to say I have x tensor sy. I mean, now from the two Frobeni, I have a map into x Tate Cp tensor sy Tate Cp. And then from the fact that the Tate constructions lack symmetric monoidal, we get a map x tensor y Tate Cp. So that's how, I mean, so in other words, the tensor product is just the underlying tensor product of spectra, and it fortunately works out that the structure maps all go exactly the right way, so that this becomes a symmetric monoidal infinity category. And again, I'm not going to say much about the proof. In fact, what you do is you just observe that this here, I mean, this is not quite a pullback of symmetric monoidal infinity categories, because I guess the Tate construction is not quite a functor of symmetric monoidal infinity categories, right? It's only lacks symmetric monoidal functor. But I mean, this is actually a pullback in the category of symmetric monoidal infinity categories and lacks symmetric monoidal functors. Or I mean, such a pullback is a priori only an operat, but since we didn't go into operats, this is, I mean, let me just say that this is still a pullback if sufficiently interpreted. That's the way to prove that. So instead of telling you what exactly, I mean, you know, a symmetric monoidal structure, as we've seen, is much more than just a tensor product. But instead of giving you all of that, let me just tell you what a commutative algebra is. A commutative algebra in cyclotomic spectra is given by, well, you can work this out just using this informal description of the symmetric monoidal structure that I've given you. So first, X, the underlying spectrum, is actually a a commutative algebra in the category of equivariant spectra. So in other words, it's a commutative ring spectrum with a T action through maps of commutative algebras. Secondly, there is just a map, a T equivariant map of commutative algebras from X to X Tate CP for every P. So in other words, I mean, the point is, if X is a commutative algebra, then so is X Tate CP, because Tate CP was a Lag symmetric monoidal functor. And so making something into a commutative algebra in cyclotomic spectrum just amounts to giving that map the structure of an E-infinity ring. I mean, first giving X the structure of an E-infinity object, and then giving this map a structure of an E-infinity object in commutative algebra spectrum. Or said differently, the pullback that I just erased is still a pullback if I just write C alg in front of everything. Okay, and in particular THHR for R an E-infinity ring is a commutative algebra in cyclotomic spectra. Okay, good. So now we have set up this category of cyclotomic spectra. It was just making rigorous the kind of structure we saw on topological Hochschild homology. And now let's recall that, I mean, previously we defined Tc minus R, right? So Tc minus R was defined to be, take the THHR and then the homotopy as one fixed points, right? And this you can in fact write as a mapping spectrum in spectra with T action, as we've seen, from the sphere with the trivial Z action into THHR. And what we're going to do is we will give a similar description for TC. Just that we work in the category of cyclotomic spectra as opposed to the category of spectra with T action. And remember, this was just an obvious generalization of what negative cyclic homology was. Negative cyclic homology would just be the same if I work over the integers as opposed to the sphere. Just literally this mapping spectrum. And the point is, on Hochschild homology, ordinary Hochschild homology, we just had the action by T and not the cyclotomic Frobenius. So in that sense, I will make that definition of TC precise in a second. It's just somehow the universal thing you can do taking the cyclotomic structure into account. And as such, it is a literal generalization of TC minus or HC minus. And it is not, I mean, in this course I haven't talked about cyclic homology. And the reason is that topological cyclic homology is not a generalization of cyclic homology. It's rather a refinement of negative cyclic homology. So the terminology topological cyclic homology is in some sense very misleading. I mean, it's established, that's why we'll use it, but topological cyclic homology is not a generalization or refinement or anything of cyclic homology. It's more like an analog of HC minus or like a refinement of HC minus. Okay, having said that, let me just give the definition. So the first thing I have to do in order to give the same definition in cyclotomic spectra, I have to tell you what the source is, what the sphere as a cyclotomic spectrum is. So the example is that I look at S trif is canonically a cyclotomic spectrum. And what is it? Or maybe canonically refined. So the underlying spectrum with T action is S triv. So it's just a sphere with the trivial T action. And this, in fact, it will be a cyclotomic spectrum, in fact, E infinity. Okay, so there's a unique action of the torus on the sphere as a map of E infinity rings, because, I mean, as an E infinity ring, the sphere is initial, so the endomorphisms are the point. And what is the cyclotomic Frobenius? So for every prime, the map phi p S to S tate CP is also unique, is the unit, right? Because, I mean, I said it's an E infinity ring. So it can only be the unit. And what is the unit? I.e., I mean, another way of writing the unit, i.e. the map, where I go from the sphere to the sphere homotopy CP fixed points, and then with a canonical map to the tate CP. And this map is just, I mean, SHCP is just S to the BCP, because the action is trivial, so this is pullback along BCP to the point. And it's a good exercise to check if you understand what equivariant maps are, why this is a T equivariant map, what this even means. Because one has to be a little bit careful with the action here. I mean, even though the action here is trivial, you have to be a little bit careful as to contemplate the correct action here, or maybe here. Okay, I want to leave that as an exercise. And now we can finally give the definition of TC for a ring spectrum, ring or ring spectrum. R, we define TCR to be the mapping spectrum in cyclotomic spectra from the sphere with a trivial action into THHR. So if R is commutative, then this is in fact a ring spectrum, the infinity ring. That's just generally true if you have a symmetric monoidal stable infinity category. Mapping out of the unit is a lag symmetric monoidal functor. So since this is an algebra and this is in fact the tensor unit, maybe I should have said that, this is the tensor unit in the infinity category of cyclotomic spectra. And so as a result, this is going to be a ring spectrum in this case. So TC of a ring is a ring spectrum. And of course we will write pi star TCR as TC star R. And more generally, for any cyclotomic spectrum, X, we write TCX as the mapping spectrum in cyclotomic spectra from sphere triv into X. And I guess maybe this has as a consequence that TCR is the same as TC THHR. right, by definition. I mean, this looks a little funny, but I think it doesn't possibly lead to confusion. Okay. And now I want to explicitly evaluate this formula. Evaluate this. So what is the map in cyclotomic spectrum, the mapping spectrum, from S trif into X? Well, I guess we had this mapping equalizer formula where we've seen, so what we have to do is we first have to take the map in spectra with a T action, S trif into X. And then now we have again two maps into the mapping space in spectra with T action from S trif into X tate CP. And I guess I have to take the product over all primes. Okay, so that is the formula that we get, and I guess we could even write down the two maps here. But what does this mean? Let me just write this again. So TCX, which is this, is equivalent to, well, let's just evaluate that further. So it's the equalizer of the following thing. What is the mapping spectrum in T-equivalent spectra from S trif to X? Well, that's just XHT, or TC minus in the case of THR, the THH. And then we have two maps. And what is this guy? Well, this is just the product over all P of X tate CP and then H is HT, right? And let me just give you the two maps. So, I mean, the equalizer is the same as, maybe let me write it as a fiber of two maps. So it's XHT, and the two maps I will write as, one of the map is just the canonical map. I write can. And the other one is something the way I explained from the Frobenius. So you have phi HT minus can. And what is phi PHT? Phi PHT is just a map from, well, XHT to X tate CP HT. Right, so we just raise the T equivalent map to the HT. So that's phi PHT. And then the can map is just what? Well, we just have a map from XHT. We can write as XHCP and then HT. Where this is again, really I should write T mod CP, but I just consider that, I mean, identify that again with T as a residual action. And then we just have the canonical map from HCP to tate CP. And then here again HT. So it's can HT, really. So that is this map. And I guess I should write P and P. So we do that for every prime separately. Okay. And I mean, this is just, I mean, a little exercise in terms of this pre and post composition with the maps I've written down to see that this is a description of the maps. And in fact, there's a way of writing this slightly nicer, which I will give you now. And that uses the following theorem. Assume that X is bounded below. Right, X is a spectrum with T action. So by bounded below, I just mean that the negative homotopy groups vanish at some point, like pi n of x is 0 if n is small enough. Okay, it's, for example, connective, but it could also have a bunch of negative, finitely many negative homotopy groups. Assume that x is bounded below with t action. Then the canonical map, well, I claim there's always a canonical map from the Tate construction for T into the Tate construction for CP upper HT. And so the claim is that exhibits this map, which exists without anything, exhibits the right-hand side as the P completion of the left-hand side. Moreover, if X is P complete, then so is X Tate T. So in other words, if X is P complete, then this is just an equivalence, because then the source is already P complete. Okay. So that's just a statement about a spectrum with a T action. And that is I will give a proof of this theorem at the end of the lecture. Let me just use this theorem for, this is something I've proven initially with Peter Scholze. I'll give an argument at the end of the lecture, as I said, but let me for the moment just use this as a black box. So as a result, if X is a cyclotomic spectrum with underlying spectrum bounded below. So that's what I will just mean by saying a cyclotomic spectrum is bounded below. Then, well, we have this map phi p ht. We can look at those maps here. Phi p ht. Phi p ht can be considered as a map from x ht into, well, I guess a priori it goes into x Tate CP ht, but this is now the same as x Tate T P complete. By the statement. And now I can also assemble all the phi p ht's for all primes together. And that will give me the following map. Phi, which is just a map from x ht into the profinite completion of Tate T, which is just a product over x Tate T P completed. Product of all primes. That's what is called the profinite completion. It can also be written somewhat more canonically as a sort of completion. Well, the profinite completion, I guess. And so I get this phi map from x ht to x Tate T upper P. And so a corollary of all of this is that we have that TCX, if x is bounded below, that if, sorry, just trying to write a full sentence, TCX is equivalent to the fiber, or maybe to the fiber of a map from XHT into X Tate T profinitely completed. And what is the map here? I guess the map here is a priori it's phi minus, and now the canonical map. But the canonical map after these equivalences, it's easy to see that this is literally just a canonical map, which I mean the canonical map from HT to TT and then followed by profinite completion. So TC is actually the fiber of that, and maybe it would be better to write it as an equalizer of XHT, and then you have two maps, phi and can to X TT hat. The reason it's better to write it as an equalizer is because it's obvious if X is an algebra that this equalizer is an algebra, right? Whereas for a fiber in general it's not true, but I mean of course if it is the fiber of a difference of two algebra maps, it's also true, but the proof is, well, then it's just the equalizer. And of course, I mean, as a result, we also have THHR, TCR. TC of a ring spectrum R is just equivalent to the equalizer of a map from TC minus R. I have two maps, namely a map phi and a map can to TPR, profinitely completed. Okay, and this is maybe the one formula that I care about. And instead of going through this category of cyclotomic spectra and this kind of theorem on all that, I could have just given that as a definition and should have maybe. But this only works if R is connective. So R a connective ring spectrum. Or at least R is such that THHR is bounded below. Otherwise you'd have to replace this term by this infinite product TCP-HTs, which is also fine. All right. And this corollary is immediate from what I've done before. It doesn't require any proof. Okay, so let me just say one word about the non-affine situation. So this is just for those of you who are interested in schemes as opposed to just rings. So for this I'll just restrict to ordinary rings. I mean, of course TC can be evaluated on ring spectra, but we care about the case where R is actually a ring. And then, of course, more generally, you might want to sort of go to non-affine schemes. So for X, a QC-QS scheme, quasi-compact, quasi-separated, we define THHX just to be the limit over all U in X affine open of THH OX. Right, so in other words, we're just saying for affines it is actually just OX, and for non-affines it's just the limit over all covers by affines. And the QC-QS condition actually ensures that this is essentially a finite limit. So then we get that TC minus X is just defined to be, well, I guess you just take THHX and you do HT. But this is then also, because I said this is a limit, so it commutes with taking homotopy fixed points, affine open of TC minus OX. And TPX then just to be defined as THHX TT, and again, and here I'm using that this is essentially a finite limit, affine open of TP OX. Right, so this is what, I mean, being quasi-compact, quasi-separated ensures this is like a finite limit. And then finally I have that Tc of x is then defined to be Tc of the cyclotomic spectrum THHX. And this is now also the inverse limit u in x as before, Tc OU. But it is also the equalizer of two maps Tc minus x into Tpx. And I guess I should sort of profinitely complete. That doesn't matter. I mean, this will just sort of, I could have sort of also put the profinite completion anywhere here. And right, so again, this is going to be the non-affine case. And let me end this lecture, or the official part, before I go into the proof of the theorem, with a remark. And the remark is that one can show that for x n-connective, that meaning that the homotopy groups below degree n vanish. So pi n is the first homotopy group, and then possibly higher ones, that Tcx is the p-completion of or I should say the p-completion of Tcx, which I will also denote as Tcx, Cp. So x is not a scheme here, x is a cyclotomic spectrum, that this is n-1 connective. In particular, Tc of a ring for R a ring or connective ring spectrum is -1 connective. So it's not quite connective. It might have a pi -1, but nothing below that. And I mean, I guess I should say something like, well, let me not say that. If x is a scheme, then I mean, this is 1 less than the, I mean, pi, it's -n-1 connective, where n is a coherent homological dimension of x. This is just follows from this limit formula, where you see that you cover by affine opens. And then. Okay, so that finishes what I wanted to say about the definition of Tc. Next time I will use this definition and calculate Tc in a bunch of cases. So that's really what is interesting about this topic, that you can actually calculate that stuff. Even though now it might appear to be somewhat complicated, it's actually calculable. Like we will calculate it for Fp, for example, next time. But for today I want to prove the theorem I had on the board, and let's remember what the theorem was. Theorem stated that if x bounded below with t action, then that x tate t, I mean, let me sloppily write that that x tate t p complete is equivalent to tate cp ht. And it also, if x is already p complete, then the p completion is unnecessary here. Right, so how do we see that? So proof. So first observation is that both sides sides of star are exact functors, are exact in the x. And, right, this is clear because all of the functors involved are exact. And commute with Postnikov limits, with the Postnikov tower. So that means I write x as a limit of its Postnikov truncations, tau lesser equal nx, the inverse limit, and then the claim is that I can pull the limits through all these constructions. And that is a slightly non-trivial claim, and that, I mean, for this, I won't give an argument for that. You'll have to contemplate the connectivity in the resulting tower. So all these functors go in some sense well with connectivity, somehow. I mean, Tate is somehow a mixture of homotopy orbits and homotopy fixed points, and homotopy fixed points being itself a limit commutes with all limits, and so you can reduce to checking that for the homotopy orbits, but for the homotopy orbits, I mean, those preserve connectivity. Because the Postnikov towers get higher and higher connective, the result follows. Okay, so both results, so thus you can reduce or assume to X being an Eilenberg-MacLane spectrum in a single degree. Right, because, I mean, the Postnikov tower has subquotients being Eilenberg-MacLane spectra, and because it's an exact functor, we shift all of those in degree 0. And solving A by a two-term complex of free groups, we can assume that A is free. And by the way, I should have said, this is of course, I mean, X is a spectrum with a T action, so this has a T action, but the T action has to be trivial, right? Because the T action on a spectrum in a single degree is trivial. So it's HA with a trivial T action. So we can assume A is free, and well, I guess now comes the first step. So in my initial statement of that claim, I stated that the right-hand side is p-complete because it exhibits, it is the p-completion of the left-hand side. So first thing is now check that, well, X HA Tate CP is actually p-torsion. And this is classical Tate homology. And Tate homology of any billion group is actually p-torsion. Tate CP homology of any billion group is p-torsion. Thus, p-complete. And thus it follows that X Tate CP HT is p-complete. And if X itself is p-complete, then you also see that the left-hand side X Tate T is already p-complete. Because in a billion group being p-complete is just implies that it's derived p-complete. Actually, the way I stated it has to be derived p-complete, and then you see that Tate T is also derived p-complete. Okay, so that actually proves already the completeness assertions I made. And now we just have to check that this is an equivalence for X being HA and A being torsion free. But then we can check that this is an equivalence modulo P after taking mod P. Right, or the cofiber by multiplication with P, but because this is something which is true, if you have a map between P-complete spectra and you want to check it's an equivalence, you can do that after reducing mod P. So, as a result, can assume A is an FP vector space. Right, because I just pull the mod P reduction through everything, and because A was torsion free, this is going to be an FP vector space. Well, so A is a direct sum over FPs. And now the last reduction is both sides of star commute with the direct sum over Fp. So more generally, both sides commute with uniformly bounded below direct sums. So direct sums of connective guys. So this means finally we can assume A is equal Fp. Okay, so this reduces me to proving this equivalence if A is Fp. Let me do that. Okay, so we have to compare the homotopy groups of HFP Tate T, which we can compute, which are actually FPT plus minus for T a generator in degree -2. So that's a ring spectrum, in fact. I'm using here that everything is a ring spectrum. The action is the trivial action, so that's the action through ring maps. And we have to see that this spectrum is actually equivalent. I mean, because it's already p-complete, we can drop the p-completion. This spectrum is actually equivalent to the spectrum HFP Tate CP HT. And here, actually, there's one important thing to take into account. This action of HT is a residual action. So we have the trivial action of the group T on HFP. We take Tate CP. Then this has a residual T mod CP action. And even though the initial action was trivial, this residual action will be non-trivial. That's actually very important to keep in mind and very easy to get wrong. But the claim is that this is a non-trivial action, and this actually we have to show see that this is actually also Fp adjoint T plus minus, and then we're done. Why are we done? Well, because, I mean, the canonical map, as I said, everything is a ring here, and the canonical map from here to there is actually a ring map. So I didn't really talk about this canonical map, but it is a ring map, and any ring map from here to there is in fact an isomorphism. That's the point. So this is because, I guess, T is a unit, so it has to be sent to a unit here, and so it's an isomorphism. So in fact, it suffices to abstractly show that this is isomorphic to that at the ring. And so how do we do that? So recall or note that we can look at the homotopy groups of HFP Tate CP. That's a Tate cohomology. And what is that? That is actually, and I guess now I have to make a case distinction. Let's say, I guess P odd and P equals T, 2, P odd. P equals 2 works actually the same, just slightly differently. And so this is actually Fp adjoint T plus minus, where T is again in degree -2, and tensor an exterior algebra, where this exterior generator is in degree -1. This just comes out of the, I mean, in negative degree, this is just a group cohomology. That's where this guy comes from. And for P equals 2, you just get a polynomial ring on a generator in degree 1. So somehow there you have an extension, a multiplicative one. Okay, and what will also be relevant is the homotopy fixed points, HCP, and that is just the negative part. So Fp adjoint T tensor lambda Fpe. And now what I want to do is I want to use the homotopy fixed point spectral sequence HFPSS to compute, well, I guess the upper guy, pi star HFP Tate CP HT. And what is this homotopy fixed point spectral sequence? It takes the following form. Well, we just have the cohomology of CP infinity with values in this guy. So this is going to be Fpt plus minus tensor lambda Fpe And then the cohomology generator from CP infinity is going to be some x, where now the x sits also in degree -2. So I'll draw that spectral sequence in a second, but so that's the spectral sequence. But as a warm-up, we want to compute the homotopy fixed point spectral sequence for the thing x HFP HCP upper HT. And which form does this take? So, let me write it like this. So this takes the following form. So the E2 page in this case is just going to be FPT tensor lambda FPE, and then again, I mean, same generator FPX. And this will converge to the homotopy groups of this guy. But the cool thing is now the following. So remember, we have taken the residual action here. So it's really T mod CP. So as a result, because this is first taking HCP and then HT mod CP, this is the same as just taking the homotopy fixed points for HT. Right? That was one of the things about residual actions. That's how the homotopy fixed points combine. And so this is actually, this guy we can of course compute. This is just the FP cohomology of CP infinity. So this is just going to be, let me write this as FP, adjoint T. And I guess, yeah. I mean, at this point, this is a priori different T than that. But we know where this spectral sequence converges to. And now let's stare at how the spectral sequence looks like. Well, I mean, the way I want to depict it is I want to write it as an axis here and an axis here. And the whole spectral sequence, I'm using homological Serre grading, so the whole spectral sequence sits in this quadrant here. And what happens is here I have the homotopy groups of the guy in the middle here. So this is going to be, I have an E here, my E. Then I have, this is 1. So every dot is going to be an FP. So I have my E, I have my T, then I have ET, T squared, and so on. And then I have my X here in degree 2. So this is 1. So here I have X, XE, XT, XET, and so on. This is in degree 2. And then I have X squared, and again it like creates a tower like this, and these are also FPs. All the dots are FPs. Okay, and the way I used my grading, so the differentials go like this. So from here to there. So that's a D2 differential, and then the D3 would go from, I guess, from here to there, and so on. So there can't be, you see immediately there can't be a D3, but there could again be a D4. A priori, for degree reasons, x3 and so on. And the point is the following, that the total degrees are just those diagonal lines. So that would be total degree 1. And of course 1 is going to be cycle, everything is a multiplicative spectral sequence, so this will just survive and give me 1 in here. But now what about this E? Well, this E can't survive because this is even. So there's no way the E can survive, so it has to support a D2 differential because all other differentials would go much higher. So the only differential which can kill E is the D2. So this will exist. So D2 will send E to actually a unit multiple of x. So D2 of E is x. And now D2 of x is 0. There's just nothing this can hit, right? So as a result, I also see that I do as well have a map like this, a differential like this, a D2 differential. And then multiplicatively, I get all sorts of differentials just by applying the multiplicative rule. And then I also see that there can't be a differential from here to there, because otherwise, if there was a non-trivial differential from here to there, then I would immediately contradict the fact that D2 squared is 0. So this has to be the 0 differential. And as a result, I see that I get a completely periodic pattern like this. And so what happens is after D2, there's nothing left on this left-hand column. So the only things that are left sit on this axis, namely t squared, and so on and so forth. And that works out perfectly, right? In that case, I immediately get FPT. Okay, that's how this homotopy fixed point spectral sequence looks like. And now, let's look at the Tate spectral sequence. So what happens in the Tate spectral sequence is that on the E2 page, I just replace the t by t plus minus. So as a result, I'll just get up here E t to the minus 1. Here I get t to the minus 1, et to the minus 2, t to the minus 2. And then I get the same tower here. The point is that I have a map of spectral sequences from the homotopy fixed point spectral sequence for this guy to the homotopy fixed point spectral sequence for the Tate guy. And as a result, I can just import the differential. So also in the Tate spectral sequence, I have to have that d2 of E is this, d2 of t is 0, so d2 of E is actually x up to a unit, d2 of t is 0, and d2 of x is 0. I guess d2 of x is 0, have to be a little bit careful. So what you do is actually go way down here. You multiply x by multiples of t so that d2 of x would land up here and then it's 0. Because a priori, if you only deduce it for the thing up here, it could hit something in the Tate spectral sequence because this didn't lie in the homotopy fixed point spectral sequence. But as you go down, far down here, it has to be 0. So you immediately get those three differentials also in the Tate spectral sequence. And then if you think about multiplicative properties, and that's a very good exercise, then you'll see that you exactly get the same kind of pattern. Sorry, maybe not this. Up here. And again, you see that everything gets erased. This pattern just periodically continues to the Tate spectral sequence. Because t and t minus survive, that's another reason. You just continuously. So as a result, you see that after the d2 differential in this other spectral sequence, sorry, I misspoke, it's not a Tate spectral sequence, also a homotopy fixed point spectral sequence. The input is just Tate. Then you see that there also immediately, you see that the only thing that survives to be the E3 page are just those multiples of t. So you just get that this converges to t plus minus. There's no possible extension problem, so as a result, we've computed the thing we computed to be fp t plus minus, and that finishes the proof. Okay, thanks very much for listening, and next time we'll go through TC calculations. Thank you.